In this video, I will be teaching you about one of the challenging parts in error analysis. Now, when it comes to finding your standard deviation, mean, and everything, I will skip that for this video because you can easily read and understand that. But the major one I want to talk about is, let us say you are given an unknown that you are looking for, and it is being determined in terms of so many other things. For example, if you do the experiment in simple pendulum and you have t equals square root of 2 pi L over g, you know that by the time you make g the subject of formula in this place, you can express g in terms of every other variable here, such that g will be equal to 4 pi squared L divided by the square of the period. Now, you will have the error according to L, you have the error according to T. So how do you now find the standard error of G? So that is what I want to explain in this particular video. Now, before I proceed to this, let me quickly use the example of, I'll start with one function. Let us say that f is defined with respect to a function x in this manner. So what you need to do is that you need to find the derivative of f with respect to x. So what do I mean by that? Find the f dx. Now, what is the f dx? According to your derivative rule, the power rule, the derivative rule, which is the power rule, says that if you have this, you multiply n with a, so you have na, then you subtract 1 from n. That is how you find your derivative. So the power here is 1, and the coefficient here is 1. So 1 times 1, we have 1. And then when we subtract 1 from the power, so what we get is, so we have 1 multiplying here. And when we subtract 1 from the power, we have 0. So at the end of the day, 1 minus 1 is 0. So x raised to power 0 is 1. So at the end of the day, derivative here is 1. So I will write 1. So the next thing I want to do here is that I want to cross multiply. So when you cross multiply, you have that df equals dx. So you can simply change this to change in f equals change in x. So meaning that if the function you are given is in terms of x and you know the error in x, so for this particular one, the error in x is the same thing as the error in f. Let me make it a little bit more complicated. What if I have f equals 1 over x? Now in this place, we'll use the same approach, but here we will use the law of indices to rewrite this first. This is the same thing as x raised to power negative 1. So therefore, when you find the derivative of this guy, the f dx, according to this power rule, negative 1 will come down to multiply. So you have negative 1, then x, you have minus 1 minus 1. And this will be negative x raised to power negative 2. If you like, you can rewrite this in using indices, that the f dx equals negative 1 over x raised to power 2. So what do you do next here? Cross multiply. So you have df equals negative dx over x squared. So finally, what does that mean? This means that your error in f equals minus change in x over x squared. The implication of this is that if you know the error in x and you want to determine, so f is defined as 1 over x. So if you know the error in f and you want to determine the you know the error in x and you want to determine the error in f, just use this expression. That would be minus change. Now this is now the only issue that we have here. We will always ignore the minus sign, because when calculating error, don't forget, we always use plus or minus to represent it. So the minus does not really matter. So you can always ignore the negative sign that you get when you are done with your calculation. So just error in x over what is the actual value of x, then you square it based on your result. So for instance, now let's say in your experiment, what you have determined, you got x1, x2, and you got plenty of x's, and then you are able to find your error in x. Of course, your average value will be the x that you will use in this place. That is how you determine the error. So you know the error in x, and then you know the value of x. So you can divide them in this manner, ignoring the minus. That will give you the error in f. Now, what if this function is now dependent on more than one variable. What if f equals x over y? If f equals x over y, so the first thing you want to do is that you find your f1, that is, assume that there is no y, assume that it is only x you are dealing with. So what do you have here? So f1 equals x. If you follow what we have been doing so far, that means that you have the f1 equals the x. Now, but in the case of f2 now, f2 will be 1 over y, which implies that f2 equals y raised to power negative 1. Now that means that if you find your derivative of f2 with respect to y, that will be minus y raised to power minus 2, which you can rewrite as minus 1 over y raised to power 2. Don't forget, I don't need the minus part, so I can simply rewrite this as the f2. When I cross multiply now, dy will go up, so I will have dy over y squared. Now, once I'm done with these two guys, now don't forget what I've written up here, that is s is always equals to this. So s equals, so let me first of all get this first guy. So s1, what is s1? S1 is just you simply dividing what this guy is over what the original function is. So the x will change to change in x over what's the original thing, x. That one is settled. Let's get our s2. Our s2 is, what is the change that we got here? The f1. So the f2 in this place is what? So the y will change to change in y. So that's change in y over y squared. Now, divided by what? What's the original thing? The original f2 is what? 1 over y. So divided by 1 over y. When you perform this, you have change in y over y squared times y. So y cancel what? This. So at the end of the day, you have your s2 equals change in y over what? Over y as well. Now that we know s1 and s2, we can then use what I've taught earlier. S is always going to be f multiplied by square root of s1 squared plus s2 squared. Don't forget what this f is. F is the actual original function, which is x over y. And then this would be f. You can decide to leave it as f or just put x over y if you like. Then square root of s1 is change in x over x squared plus change in y over y squared. Now let's go back to what I used as an example earlier. I said in the simple pendulum experiment, when we make g the subject of formula, g is going to be 4 pi squared multiplied by L, everything divided by the square of the period. The first thing you want to do here is that you want to even forget about the constant term. What I mean by constant term is that things are just ordinary numbers. They are not varying at all. They are not changing. So leave them. Now, in this situation now, so we have G that is varying in terms of L and period alone. So according to what I taught you, so the first thing you do is to define G1. G1 will depend only on L and forget about the period part. So G1, you can see L is on top, so G1 will be equals to L. So you find your derivative of G1 with respect to L, and that would give you 1. If you differentiate L, you have 1. That is, derivative of G1 with respect to L, you have 1. Then here, you can cross multiply. That means that the G1 equals what? Equals the L. And with that, you can easily just know that your change in G1, your error in G1 is the error in L. So the next thing you want to do here is that you want to find your G2. Now G2 will depend only on the period and you will ignore everything about L. So as you can see, it's at the denominator. So, and I can't just write over something. So I just have to put 1 over the square of the period. From what we have been learning so far, G2 can now be written as t raised to power negative 2. So let's find the G2 dt now, that is with respect to the period. So when you go by what we have done, that will be negative 2 coming back here, then t raised to power minus 2 minus 1, that will be minus 3. And if you write this very well, you have minus 2 over t raised to power 3. That is if you use indices. So going forward, I told you that we need to bother about the minus sign. That implies that we cannot write the G2. If I cross multiply and take dt to go and make this, that will be 2 dt over t raised to power 3. And you can easily change that from that is error in G2 equals 2 times error in the period over t raised to power 3. Now, what's the next thing we need to do? We need to find our S1. Our S1, like I've taught you, is simply the change in the first function over what the actual first function is. And what's the change in the first function according to what we have here? That is what? Change in L over what's the actual first function, which is G1, that is L. So you are done with that. Let's find our S2 as well. S2 will also be the what? Change in the second function, which is change in T2 divided by the second function, which is what? G2. Now, what is change in G2 according to what we have here? That is 2 change in T over T raised to power 3 divided by what is G2? Originally, G2 is 1 over T squared. So you put that here, 1 over T squared. And if you do this very well, you have 2 times change in T over T raised to power 3 multiplied by what? T raised to power 2. This will cancel 2 of these and you'll be left with 1. So what does that mean? Your S2 will become 2 times change in T over what? Over T. So our standard error for G now, which is the actual function we are dealing with, is going to be, so you have the function G itself multiplied by square root of S1 squared plus S2 squared. And what is that going to be? That is G square root of, what is S1? According to S1, we have change in L over L. So that's change in L over L all squared plus, what is S2? S2 is this 2 change in T over what? Over T all squared. Don't forget what this G is. This G is the original function, which is this entire guy. This time around, you will not ignore the 4 pi squared. You will actually include the 4 pi squared because it's part of what you are dealing with. So this would then be the error. So you can just practice more of this. And if you need more help, you can drop it in the comment or send a direct message to me. Don't forget to like, subscribe, and follow for more content like this. I'll see you in the next one.